method. Okay, let's wait for let's connect try to connect my iPad. It's not connecting for some reason. Let's see again. Who has said this? The proof of D'Alembert principle. Please explain what is there after dynamic equilibrium. Okay, I'll tell again. Okay. Okay, so in the last class I told you about D'Alembert's principle. So I told you that when the system is in dynamic equilibrium, this quantity, this F(Ee) minus Pi dot delta Ri, this is equal to 0. Okay. Okay, one thing I forgot to mention, this quantity, this Pi dot, this is also called reversed effective force. This is also called reverse effective force. So this statement is basically tells you about when the system is in dynamic equilibrium, that the applied force, that this combination of applied force and the rate of change of momentum due to inertia. Okay, and if you project these two on the virtual displacement, this should be equal to 0. This is basically similar to your Newton's laws, but it is framed in a different way. In terms of the virtual displacement, not in terms of the real displacement. If you think this quantity, first term is the applied force, second term is this is the a force due to inertia. So when the system is in equilibrium, these two terms should be equal, and that is the statement of the D'Alembert's principle. That the forces due to inertia and the externally applied force, okay, their combined virtual work should be equal to 0 when the system is in equilibrium. When the system is in static equilibrium, we don't need to consider we don't need to consider this forces due to inertia. When the system in static equilibrium, it is simply that the external forces, they do not do any work to do any virtual displacement. But when the system is in dynamic equilibrium, this externally applied forces and the forces due to inertia, their combined work on the virtual displacement is 0. Okay, I'll give you one or two problem on this principle of virtual work and the D'Alembert's principle, so that this idea becomes little bit more clear. I have already included in the tutorial sheet. Okay, so if you if you solve those problem, it will be easier for you to understand this principle. Okay, and then from D'Alembert's principle, we derive this Lagrange's equation of motion. We derive this one, Lagrangian equation of motion. We showed you that d dt of del qj dot minus del qj, this should be equal to qj. And from these, we solve that if this generalized force, if the generalized force is conservative, if this can be derived from a potential, then this takes the form d dt of del L del qj dot minus del L del qj equal to 0. where AL is basically T minus V. This is called Lagrangian. This is called Lagrangian. And we solved one problem. We solved one problem of this linear harmonic oscillator, simple harmonic oscillator, to see how this this Lagrangian framework works. Okay. So today we will continue. We'll solve some more problem on this Lagrangian. Okay. So one of the problem that we want to solve is simple pendulum using this method. Simple pendulum. So let's say you have this simple pendulum. Okay, it's suspended from a rigid support. Okay, and let's say this is the bob of the pendulum. Okay, and this length is L. This angle is theta. Okay. Now, how do we set? How do we set up the Lagrangian in this case? Can you guys tell what we have to do? Set up the Lagrangian. Any guess what we have to do? We have done already for simple harmonic oscillator in the previous class.
Go through the energy method, kinetic energy and potential.
Yes, so we need to calculate the potential energy and the kinetic energy. So first we need to, so okay, so first thing is that you identify the degrees of freedom in this case. Okay, because Lagrange's equation of motion is not a single equation. It will the number of equation, it will depend on how many generalized coordinates are there. Okay, so first you tell me how many degrees of freedom we have in this case. That should be 1, right? And what is the generalized coordinate in this case? Generalized coordinate is theta in this case. Now tell me what will be the value of kinetic energy for this simple pendulum. Anyone? What will be the you have already done this in class 12. Please tell me what will be the kinetic energy. How will find the kinetic energy in this case for this simple pendulum? You guys want to continue this class? You guys need to tell me, okay? Otherwise, we'll not continue because you guys need to respond.
So 2 pi under root L by G.
Kinetic energy? Kinetic energy 2 pi root over L by G.
So half omega r square L square m.
Yes, so basically kinetic energy is half mv square. And here half m is fine. But v is generally linear velocity. In this case, this will be angular velocity, right? And this will be given by L theta dot. theta dot, this theta dot is the angular velocity here. And if you multiply this with length, you will get v square, right? So you get this value half m l square theta dot square. What will be the value for potential energy? How we will calculate the potential energy in this case? For simple pendulum,
mgl 1 minus cos theta.
yes, mgl 1 minus cos theta, right? Because this ideally the system, when the system is at this position at theta equal to 0, this is mgl, and this is theta, so this will be mgl cos theta, right? When when the bob is at this position, that value is mgl, and but the bob is at this angle theta, so this potential energy will be mgl 1 minus cos theta. So what will be the Lagrangian in our case? This will be L equal to T minus V. So you can see the Lagrangian is half m L square theta dot square minus mgl 1 minus cos theta. This is the Lagrangian for the system. This is the Lagrangian. This is the Lagrangian for this system. Now we want to find the Lagrange's equation of motion. Okay, let me zoom out this one. So Lagrange's equation of motion, we know that that is d dt of del L del Qj dot minus del L del Qj, that is equal to 0. So in this case, our Qj, that is basically theta. So in our case, the equation would be this equation will be d dt of del L del theta dot minus del L del theta equal to 0. So what will be the value of del L del theta dot from this expression? We know the expression for L. So what will be the derivative del L del theta dot? Del L del theta dot will be how much?
ஏன்பா
எங்கம்மா இங்க பாக்குறியா
அந்த இது இன்கம் சர்டிபிகேட் எடுத்து வை.
இல்லம்மா
இன்கம் சர்டிபிகேட்
இங்கதான் இருக்கும் நீ தேடி பார்ப்போம்
What will be the value of del L del theta dot?
குழம்பு டீச்சி ரெண்டெல்லாம் இருக்கு பார்த்து இப்ப உன்னோட சர்டிபிகேட்டோட சேர்த்து இருக்கு பாரு
Can mute this one. Whoever is this, please mute,
ரெண்டு கவர்ல வச்சிருந்தல அதுல இருக்கு
mute this one. Whoever is this. We know this expression for L. What is the value of del L del theta dot now?
ml square theta dot.
Sir, ml square theta dot.
This should not take this much time to compute this one. ml square theta dot, right?
Theta dot. Yes, sir.
And what is the value of del L del theta?
ml square
mgl sin theta.
mgl sin theta.
mgl sin theta. But then this will be plus, right? This is equal to 0.
Yes.
So what we get from here? ml square theta double dot plus mgl sin theta. This is equal to 0. Or from here you can write theta double dot plus g by L Sine theta equal to 0. And if theta is small, then you can write sine theta nearly equal to theta. So from here, then you can say theta double dot plus g by L theta, this is equal to 0. So this is your equation of motion. This is your equation of motion for the pendulum. We are not interested in solving this one in this class. We are mainly interested to set up the equation of motion. Okay. Solution is different. Solution you can do if you have knowledge on mathematics. But first you have to find out the equation of motion before solving this one. So goal of this Lagrangian or the Hamiltonian formalism that we'll do. So that is because of that in that problem we want to derive this kind of equation of motion. Solution, that is the next step that you can do from your knowledge on differential equation or from the knowledge of mathematics. Okay. Hey, whoever don't have question, please mute. Okay. Otherwise, I'll mute everyone. Okay. So this way you can solve this simple pendulum problem using Lagrangian method. Now, your one thing is that you might be asking now that you can solve this using Newtonian mechanics also. So why to do this complicated process? That answer will give in the next class. Okay, but you can see you get the same equation of motion. This you can get from simply considering the potential energy and kinetic energy and doing the Newtonian mechanics. But here we're using a different formalism, and that is also giving the same result. But it has some other advantages, particularly when you have a complex system or if you go in other kind of mechanics. So that we'll discuss in the very last class. But before that, let's look at another problem. So this problem is also called Atwood machine. This is also called Atwood's machine. So in this case, what's happened that you have a rigid support, okay, and you have a frictionless pulley, okay. You have frictionless pulley, and then two mass is hanging from this pulley. So one mass is, let's say this one is one mass, this is another mass, okay. So let's say this is mass M1 and this is mass M2. And this is hanging from this frictionless pulley. Okay. We want to set up the Lagrangian and solve the equation of motion in this case. Okay. Now you guys need to tell me how we should proceed. Okay. So first we want to find the degrees of freedom. So how many degrees of freedom we have in this case? Let's say this radius, let's say this radius is A. Okay. So first tell me how many degrees of freedom we have in this case.
Two.
Someone said 2. Any other answer?
Sir, 1.
Which one is correct? 1 or 2? Who said 1? Why this should be 1?
Sir, because the masses move independently toward downward. So, sir,
Yes, these masses are
we have,
connected. Like if mass M2 moves downward, then mass M will move upward, right? So if
sir, then
it
it,
moves by a
sir,
certain amount, mass M1 will move by same amount on the upward direction. Yes, tell me.
sir, that motion because are, sir, related with each other. Sir,
Yes,
we have only one independent equation y.
yes. So these masses are connected. So their motion is not independent. They are connected. So in this case, the correct answer is that we have 1 degrees of freedom. Okay. And what is the generalized coordinate then in this case?
Sir, y.
So how will, okay, let me tell you how to find the generalized coordinate here. It is not simply y, generalized coordinate. So let's say this mass M1 has this distance of mass M1 from this pulley, center of the pulley, this is x1, and this distance, let's say this distance is x2. Okay. Now then what we can say? We can say x1 plus x2 plus this one, this distance, this pulley, this distance, this half of this circle. This half of this circle, if you say that will be pi into a, this should be constant. That value is L. So in this case, your generalized coordinate is not simply y. You can take either x1 or x2. Either of them you can take as a generalized coordinate, because you need to only know either x1 or x2. That is the variable that you need to know to solve this problem. And x1 and x2 are connected by this equation in this case. So you can see that x1 dot that should be equal to minus x2 dot, right? If you do derivative of x1 and x2, you will get this. Or you can do double derivative also. x1 double dot, that is equal to minus x2 double dot. Now, what will be the kinetic energy for this system? Can you guys tell what is the kinetic energy for this system? What will be the expression? Kinetic energy is what? Kinetic energy half mv square. So what is the velocity for the mass m1? I need some response. Can you guys tell what will be the velocity for mass m1?
Sir, hence they are connected with same string, so the total kinetic energy will be half m1 plus m1 plus m2 or x dot square.
Yes. So for the mass m1, the kinetic energy is half mx1 dot square. I don't know whether other guys you guys can follow or not. You guys need to tell me whether you guys are following or not. If you guys don't tell me, don't respond, then it is a loss for you. Okay. Because you have to solve this thing in the exam. So kinetic energy for mass m1 is half m1 x1 dot square, and for the mass m2, that will be m2 x2 dot square. So you can see that x1 dot is equal to x2 dot. So from here you can say half m1 plus m2 x1 dot square. So let's say we are considering x1 as generalized coordinate. You can take either of them, x1 or x2, anything. So generalized coordinate you can take, let's say here we are considering x1, you can consider x2 as well, no problem. And what will be the expression for potential energy in this case? It is similar to the same simple pendulum. How much is the potential energy in this case?
So if we take the reference, the pulley is
Let's take this is the reference frame. The center of the pulley is the reference frame.
at minus m1 x1 g minus m2 x2.
Minus m1g x1 minus m2g
GS2.
x2. You can add some constant term also, but that you can set as 0. If you don't take the center of the pulley as the reference frame, you can take any other point also. But then you have to subtract the constant term. Okay. So this you can say minus m1 minus m2 g x1. Yeah, because if you take that, if you take this point, if you take that this value is constant, let's say what we have subtracted here, this part we have subtracted, this potential energy due to pi a, that part we have subtracted, that we have kept constant. Okay, in this case. So what will be the Lagrangian then? Lagrangian is L equals to, yes.
Sir, here why do we take x1 equal to x2 in the equation of potential energy?
not x1 equal to x2. x1 dot is equal to minus x2.
Sir, then sir here we for potential energy we take m1 g x1. Sir, then
You will have this additional term m2g. You will have this additional term m2g L minus pi by pi a. L minus pi a. This term you will have. Okay, we are subtracting this is constant. If you take the total length, then you will have this additional term.
oh, yes, sir, yes, yes, sir. Yes.
And this part we are setting that this is, let's say this is V0 and this is constant. Okay. So we are subtracting because that is not relevant. That you can set 0. So the Lagrangian is L equal to T minus V. So expression for T is half M1 plus M2 x1 dot square, and this will be minus plus M1 minus M2 G x1. So this is the Lagrangian. Okay. Now what will be the equation of motion in this case? So in our case the generalized coordinate is x1. So let's first find out del L del x1. What is the value of del L del x1? That will be m1 minus m2 g, right? And del L del x1 dot, this will be m1 plus
1
m2
plus m2 and to
x1
x1
dot.
dot.
Okay. So our equation of motion will be in this case d dt of del L del x1 dot minus del L del x1. This is equal to 0. Okay.
So the
So
screen become black.
yes. So okay, you guys try to solve. Meanwhile, I connect this one again. Okay. You put this value of del L del x1 and del L del x1 dot in this Lagrangian equation, and then you should get the equation of motion. So basically, whenever if we ask you to set up the Lagrangian and determine the equation of motion, basically what you have to do, you have to find the potential energy and the kinetic energy in the form of this generalized coordinate, and then write down Lagrangian L equal to T minus V, and then you can solve this. Okay. So del L, so this will be d dt of del L del x1 dot is, this is m1 plus m2 x1 dot minus m1 minus m2 g, this is equal to 0. So from here you can see m1 plus m2 x1 double dot minus m1 minus m2 g, this is equal to 0. So this is basically x1 double dot minus m1 minus m2 divided by m1 plus m2 into g equal to 0. So this is the equation of motion in this case. This is the equation of motion. Okay. In this case. Okay. Is this clear? How we are deriving this one?
Yes, sir.
Okay. I'll show one more example. Let me show one more example. Which one we want to do? Let's do this example of free particle. Okay. Let's so far we have done this kind of system where you have some constant. Okay. let's do one problem that you have a single particle, free particle in space. Free particle in space. So how you will set up the Lagrangian in this case? And let's say you have a Cartesian coordinate system. Okay. You have a Cartesian coordinate system. X, Y, Z. Let's say this is X, Y, Z, and you have some particle somewhere of mass m. Okay. Then how do we set up the Lagrangian? What are the degrees of how many degrees of freedom this particle has? If this is a free particle in a 3D space, how many degrees of freedom we have?
3.
Yes, these are 3. And what are the generalized coordinate in this case? What are the generalized coordinates in this case? What are the independent coordinates you can think in this case if you want to represent this particle?
X, Y, Z, sir.
Yes, in this case, X, Y, Z itself, they are the generalized coordinate in this case. Okay. So definition of generalized coordinate is that the coordinates which are independent. Okay. So like in this case of this mass, this two mass hanging from this. So here you can see this x1 or x2. So one of them is independent. That's why two. So okay. So in this case, x, y, z itself, they are the generalized coordinates. And what will be the kinetic energy in this case? Kinetic energy of the particle. Let's say this particle of mass m is moving with some velocity. And what will be the kinetic energy?
mv square.
This will be simple half mv square. Don't think too much. This is a free particle. We have not put any restriction, any potential, any force, anything. So this is a simple free particle that is roaming somewhere in the space. Okay. So it is the kinetic energy will be simply T equal to half m v square. And v you can decompose v into x1 dot and x2 dot and y2 dot. You can say this is half m x dot square plus y dot square plus z dot square. You can decompose the velocity in x, y, and z component. Okay. But in this case, we cannot say anything about the potential energy at this point because we don't know in which what is the force acting on this free particle. We don't know. So that's why we need to use this particular Lagrangian form here, the del T del Qj, this form. Del Qj dot minus del T del Qj equal to Qj. We need to use this particular form because I told you that if we can derive this generalized force Qj from some potential, then only we can use this Lagrangian form, this form. But if we cannot derive this potential or if we don't know the forces, then we can use this form as well. So in this case, the Qj's are the generalized force. These are called generalized force. Okay. So in this case, we don't know what is the force, but we can say that it has some 3 components. We can say that force has x component, y component, or z component, 3 component. Okay. And then we know what is T. We know T is equal to half m x dot square plus y dot square plus z dot square. So we need to find this del T del Qj dot. So what is what, and here Qj is basically x, y, and z. So we need to find del T del x. Okay. Is this clear why we are doing del T del x? Because here Qj's generalized coordinates are x, y, and z, and we have 3 variable, not one variable. Okay. So del T del x this will be, what is the value of del t del x now in this case?
mx.
Yes, sir.
Del t
No,
del x,
0, sir.
this is 0. This
0.
is 0. Del t del y, this is 0. Del t del z, that is also 0. But what is the value of del t del x dot?
mx.
Is
mx.
dot. Del t del y dot, that will be
My dot.
my dot.
My dot.
Del t del z dot, that will be mz dot.
Z dot.
So what will be the equation of motion then? So we have to write del t of del t del x dot minus del t del x. This will be equal to fx here, because qj has 3 components and we are considering x as one of the generalized coordinate. So this will be equal to fx. So you can see the dt of mx dot, this is equal to fx, right? So, and you can say mx double dot, this is equal to fx. What this reminds you, this formula? Have you seen this formula
Mm.
earlier?
Newton's second.
F equals to n.
This is basically Newton's law, right?
F equals to ma.
And now it is not only x component, you have to do the other components also. D dt of del t del y dot minus del t del y, that will be equal to fy. From here, you will get my double dot equal to fy. And you will have del t of del t del z dot minus del t del z, that is equal to fj. And you will get mz double dot, that is equal to fz. So these are basically Newton's laws. And that we should get, right? Because this is a free particle that is roaming under some force in a 3D space. So if we want to know the equation of motion, we should get back the Newton's formulas from the same thing. So these are the equation of motion. Then these are equal same thing that we have seen. Now this is in Cartesian coordinate. Can you solve this problem in polar coordinate? In plane polar coordinate, let's say this is moving in a 2-dimensional space now, this particle. Will you be able to do this one in plane polar coordinate? So what we have to do, so we have wrote t equal t in the Cartesian coordinate system. So we have to convert, so in plane polar coordinate, so how many variable will have now? How many degrees of freedom will have in a plane polar coordinate?
2, sir.
And what are the generalized coordinate?
R and theta.
Generalized coordinate r and theta. So you have to find this kinetic energy in terms of r and theta, right? You have to express the kinetic energy and potential energy in terms of the generalized coordinate. So how you will find this expression of t in the form of r and theta? So we know t is equal to half mx dot square plus y dot square, right? If you are in Cartesian coordinate, then this is true. Half mx dot square plus y dot, that is the kinetic energy. Now you know the conversion equation, x equal to r cos theta and y equal to r sin theta. So what will be x dot? This will be r dot
Minus R sin theta.
r dot cos, not simply r sin theta. This will be, first you have to do derivative for r dot cos theta minus r theta
R sin
dot
theta.
sin theta. R theta dot sin theta. You have to do derivative for theta also. And similarly, y dot, this will be equal to r dot sin theta plus r theta dot cos theta. right? So then you can replace x and y in this in here. Half m, you put these values here. Okay. These values of x dot and y dot here. And then the final expression that we will get, this should be equal to half m r dot square plus r theta dot square. This will be the kinetic energy in the plane polar coordinate. You guys should do this as a homework. What will be this expression? Kinetic energy expression in spherical polar coordinate also. Do this as a homework, okay? What will be the expression for kinetic energy in the spherical polar coordinate? Okay. Now we know the kinetic energy. Now we have to find out the forces also, because we have to use this form of this particular form of this Lagrange's equation. We have to use this form. So we need to find out this generalized forces. So in this polar coordinate, this will not be simply f r and f theta. So that you have to find out in this case. So the r component will be, we know the what is the definition of the generalized forces. I gave you in the previous class the definition of generalized force. Do you guys remember what was the formula? What was the formula for Qj? Qj, I told you this will be Fi dot del Ri del Qj. That was the expression for the generalized force. Okay. So if we want to find out the generalized force corresponding to this r coordinate, so this will be F dot del R by del R. Okay. And in polar coordinate, this vector r, this you can write r cap. Okay. And what is the expression for r cap? You guys remember what is the expression for r cap? In the polar coordinate? Anyone? What is the expression for the vector along r direction in the polar coordinate?
Sin theta, sin theta.
That was I cap cos theta plus j cap sin theta.
Oh shit.
This was the value. So what is the value of del r by del r in this case?
With respect to r,
By del r will be simply I cap cos theta plus j cap sin theta. That is simply r cap. This expression. So this force QR, this will be F dot R cap. That it is component of the force along R direction. That is for R cap. Okay. Similarly, you have to find out the component of force along theta direction. Q theta. We can define this Q theta as del R. And here the generalized coordinate is theta. So this will be F dot del R by del theta. So now we have to find out this expression del R del theta. So now I told you this will be del theta R cap. And R cap I told you that this is R I cap cos theta plus j cap sin theta. So you can see, you can take R outside. This will be minus I cap sin theta plus j cap cos theta. And what is this expression? Do you remember? What is this expression? Minus I cap sin theta plus j cap cos theta in polar. This is the unit vector along theta direction. This was theta cap or E theta cap, whatever you want to tell. So this is R theta cap. If you do derivative of del R del theta in the polar coordinate, you will get R theta cap. So your Q theta, this is basically F dot R theta cap. So you can say R F dot theta cap. So F dot theta cap means component of force along theta direction. So this you can say R F theta. Okay. Is this clear why we are getting these two different expression, FR and F theta? I'll give you some more problems in polar coordinates. So if you guys don't get how these derivatives are working in polar coordinate, so you guys need to tell me at this point. So basically you need to find the generalized force along that particular direction. And so this is the expression, and then you do simple derivative in the polar coordinate. Okay. So now we can go back. So now we know what are the expression. We know kinetic energy. Kinetic energy is given by half m r dot square plus r theta dot square. So, and we know this qr, this is equal to fr, q theta, this is equal to r f theta. Now we have two generalized coordinates here, r and theta. So we need to find out both del t del r, del t del r dot, and del t del theta, del t del theta dot. So what are this expression? Can you guys tell me quickly what will be this expression? Del t del r. What will be the value of del t del r?
half m theta dot square.
Half m theta dot square. Del t del r? No. Yes. Del t del r half m theta dot square. Similarly, you find out what is the expression for del t del r dot. What will be the expression for del t del r dot?
M r dot.
I've made some mistake somewhere. This is r theta dot square, r square theta dot square. Let me check. We made one mistake. This should be r square. This should be r square in plane polar coordinate. This expression will be r square theta dot square. This kinetic energy, final kinetic energy expression. Okay. So this is r square theta dot square. This should be r square theta dot square. Okay. Okay. So this will be then m r theta dot square, and del t del r dot, that this will be m r dot. Del t del theta, this is equal to 0. There is no theta dependence, and del t del theta dot, this will be m r square theta dot. Okay. So what will be the expression? What will be the equation of motion? D dt of del t del r dot minus del t del r. This is equal to fr. So d dt of del t del r dot, that means m r dot minus del t del r r theta dot square. This is equal to fr. So you get r double dot minus r theta dot square. This is equal to fr. Okay. And similarly, you have to do also, and this is one of the equation. This is one of the equation. You should also get for del t del theta dot minus del t del theta. This is equal to general. This is basically equal to q theta. Q theta. This is equal to r f theta. And what is del t del theta dot? M r square theta dot. So d dt of m r square theta dot minus 0. This is equal to r f theta. Del theta is 0. And you then solve what is the expression. This will be m r square theta double dot plus twice m r dot theta dot. This is equal to r f theta. So these two are the equation of motion in this case, in the free particle. Okay. Is this clear what we have done in this case? Is this clear? What we have done for this plane polar coordinate? This is simple mathematics. We have two coordinate. So we have written this Lagrange's equation of motion. For there two equation, two generalized coordinate. You have two equation. Okay. Two equation of motion. You have two equation of motion. Okay. Okay. So tell me quickly if you guys have any questions so far on this, or if you guys can follow. I'll share you the notes, but tell me quickly.
No question, sir. No question.
You guys check, these are simple mathematics. When you start from this Lagrange's equation of motion, and then you convert in potential and kinetic energy in terms of generalized coordinate, you guys should get then the equation of motion. Okay. I'll give you couple of tutorials so that you guys can practice and you guys get familiar with. Okay. Any question? I'll close this session. Okay, if not, okay, then okay, let's end it here today, and then we'll meet again on tomorrow. Not tomorrow, on Monday. Okay. Okay, guys, then bye bye. We'll meet on Monday again.